All right. Thanks for coming to Deep Learning Classics and Trends. We just passed our 6-year mark. Actually, this is our first session in the 7th year. And today, instead of having one speaker, we have a whole team. It's composed of Ron. Is it Ron? Ron?
Yeah, that's perfect, Ruan.
Ron, Sasha, and Colum, coming from the InstaDeep team of MARL, multi-agent RL team, and they're here to present this paper and this framework called MARL, if I remembered right. Okay, take it away, team.
Right. Thank you so much. And thank you so much for having us. It's a pleasure to be here. And we feel really privileged and honored to be able to share with you guys today. Yeah, my name's Ruan. I'm based in Cape Town in South Africa. I work for InstaDeep as a research engineer, part of this effort to build out this multi-agent RL reinforcement learning software ecosystem in JAX. So before we sort of start, I just want to mention a little bit, like, this is the team that's currently actively maintaining the software that we're going to be speaking about today. But this is actually work that's been going on for a very, very long time. Like Callum briefly mentioned, like our multi-agent research been going for 5 years, and there have been like active maintainers that have been in-house over the years, but also there's been lots of contributors to this, both in-house and externally. And also recently, there's this really nice resurgence in the community as well, with releases like JAX-MARL, for example, and also Pure JAX-RL doing amazing work in multi-agent RL and using JAX for reinforcement learning. So really, we feel like we're part of a big community that's pushing for driving the field forward. A question that you could ask is why? Why do we want to build out this entire software framework? And it really stems from the fact that we want to solve really hard multi-agent problems. And if we want to solve these, we're going to have to push the research frontier. And in general, multi-agent reinforcement learning is a field that requires lots of software development. And so, I mean, deep learning in general, but we really then want software that's reliable, it's flexible, it's easy to work with, but also that can scale to large problems or large compute. But then also we want our tooling to be stable, and we want it to be maintained, but then also we want robust evaluation methods. And so the reason we want to put all of this together, so we do research that will stand the test of time. So it's because of this that over the past couple of years, we've been building this entire software ecosystem built on JAX for multi-agent research that is built on these 3 pillars. The first being stable and maintained software tools, which we'll touch on. This comprises environment suites and things like replay buffers and evaluation tools. And then our second pillar being this easy starting point for research, which is really these repos that contain algorithmic implementations that you can hack with and build from. And then the third pillar, which we refer to as community artifacts, which is these open source multi-agent RL datasets, statistically robust benchmarks and baselines, and then all of this culminating in impactful research that we believe will be reproducible as well. So this ecosystem is built on JAX, like we mentioned, but to just give you a little bit of a primer on JAX, it's becoming more and more popular as time goes by, but just for everyone to be on the same page, essentially in a nutshell, JAX is NumPy that can be differentiated and can compile down to XLA code to run really, really fast on modern accelerators like GPUs and TPUs. JAX being functional, it has these transformations that you can do to functions, and 3 of these that we're going to touch on today is JIT, VMAP, and PMAP, with JIT being just-in-time compilation, where essentially some functions compile down to XLA code to run really fast on the accelerator. Another transform being VMAP, which essentially, if you have a function that can operate over a single input, if we transform that function with VMAP, it can operate over a batch of inputs. And then similarly, there's PMAP, which you can think of really as VMAP for parallelization, where you can run this code over multiple devices really, really easily. So just to go back on what this ecosystem is that we're going to talk about today, and its 3 pillars, which are the stable and maintained software tools, easy starting points for research, and then these community artifacts.
Awesome. Thanks, Ran. Hey, everyone. So I'm Sasha. I'm a research engineer at InstaDeep, and I've mostly been working on Jumanji and Marva. And to start with, Jumanji is our suite of industry-style RL environments, and specifically, they're entirely written in JAX. So the reason that's specifically that them being written in JAX is super useful is because if you have an environment and a algorithm that's entirely written in JAX, you're able to put them directly both on an accelerator and never have to have that CPU GPU communication overhead. So that's kind of a large amount of what this ecosystem leverages and how we get a lot of our speed up. So just to kind of quickly take you through the code of what kind of using Jumanji might look like. It's pip installable, so kind of very standard for any library. Can't go to the next slide. Cool. It's got a familiar DMN API. So if anyone's ever used the kind of standard DMN environments, you've got your make function and you return time steps and the like. So slightly different to Gym. Next, you've got reproducible rollout. So this is a feature that kind of comes baked in because it's a JAX-based environment suite. And what this is that because in JAX, every random call needs to be seeded, as long as you start with the same seed and pass in the same actions, you're going to get the same observations and same rewards out from the environment, which of course is super useful for reproducibility. Then of course there's rendering, and you can make nice GIFs and visualize what your agents are actually doing. And finally, again, because it's a JAX-based environment, you can JIT and PMAP and do all that kind of nice stuff and get some really nice speed ups. So just to take you through what's in Jumanji. Cool, sorry, it's a bit of a lag on my side seeing the output. Yeah, just to take you through what's in Jumanji. So we have a whole lot of environments, and specifically, Jumanji is not only a multi-agent RL tool, or suite. It's got a whole host of RL environments, single and multi-agent. But we thought, we would start off by implementing a set of existing multi-agent environments, just so that we could have some baseline to compare to and see, is it worth this investment of re-implementing these environments? And indeed it is. I will show you a bit later some kind of nice graphs that show the speed up you can get. But these two specifically are from the Edinburgh lab. It's robot warehouse and level-based foraging. Then, we thought, we shouldn't stop there. We should continue to, implement new multi-agent environments. And so we've come up with these three as an example. I think there's a couple others in Jumanji that's specifically cleaner, where a couple of agents that need to clean this maze. Connector, which is sort of a PCB or a simplified PCB routing environment where you've got to connect to a target, but also not like overlap the wires. And then multi-capacitive vehicle routing, which is basically multi-agent traveling salesman problem. Cool. So that's Jumanji, and how that fits into the ecosystem is that it's really the API for Marva, which is what I'll chat about in a bit. But we really use this as kind of our baseline API or backend API for Marva. And what Jumanji specifically gives us is fully JITable training loops. So because it's all written in JAX, you can JIT the whole thing end to end. And like I said, you don't have to do any CPU to GPU communication. However, Jumanji isn't the only environment suite that we support in this ecosystem. We basically support any JAX-based environment that can conform to Jumanji's API. So that's really any JAX environment suite. We already support JAX-MARL, which is this quite cool new framework, and then also another environment called GigaStep. So yeah, the next kind of item in our ecosystem I'm going to chat about is Marva. This is sort of our collection of algorithms yeah, also all written in JAX, and as I said previously, uses that whole Jumanji API. The big difference between Jumanji and Marva is that Marva is not intended to be pip installed like Jumanji is. So Jumanji we're kind of envisioning as this statics tool that's well maintained, but you as a researcher shouldn't really ever need to hack it or get into the super inner workings. But with Marva, we're expecting quite the opposite. It's really written in that kind of clean RL style where we're expecting you to clone the repo, you to hack around the files, you use it in your kind of day-to-day research as a starting point to kickstart your research. And so one of the things that I've said a couple times is that Marva's pretty fast. Oh, okay, there we go. Yeah, so that Marva's pretty fast, and the way that we get the speed is that we use the Anakin framework. So that's something popularized by DeepMind a couple of years ago, and it's something that you can do when you have both your environment and your algorithm written in JAX. So to zoom in on this graph, because it's quite busy, you've got firstly kind of 3 layers of parallelism. So the first thing that we do is we VMAP over the end steps. So that's basically akin to like your multi-process wrapper, where you're doing multiple end steps in parallel, and then you're passing that through your network as a batch, and you're getting up multiple actions. So nice speed up there. But then we go a step further where we VMAP the act learn loop, and basically what that does, there we go, is it basically produces like multiple gradient updates, and even more data and even more speed up. And then we take that a step further where we team up over all of this, so that can then be done over multiple devices or TPU cores, and yeah, basically producing just a massive amount of data. And then what we do with all these output gradients is we then mean them, and use that kind of mean gradient to update the model. And really what this allows us to do is one of 2 things: either do easy problems really fast or actually attack hard problems, because it allows us to produce the amount of data required in the short amount of time span you would need to kind of tackle these kind of problems. So just to dive a little deeper into like what Marva offers, basically we've got specifically algorithms. We've got PPO, soft actor critic, Q learning all the way to QMix, and then the recurrent and centralized or decentralized versions of these where needed. Again, we support multiple JAX-ends. I think it's 10 at this point, from multiple different suites. We've also got, as I mentioned, a research-friendly code base, so clean RL style, where everything's really single file implementation, and the core actual algorithm logic is only a couple hundred lines, which really we hope will encourage researchers to use this as a starting point and kind of hack from there. Then you get some benefits. There we go. Using Marva. So firstly, that your starting point works. Well, hopefully it does, because we've tested it for you. But also we've built in certain things to all of these algorithms. So other than them being very fast and parallelized, they've got robust evaluation built in. And there's, when you clone Marva, you get a suite of kind of general multi-agent RL utils, as well as like networks and checkpointing and logging, and all of this comes for free basically if you were to start your research from just a PPO or a soft actor critic or QMix or something like that. Cool. So I've told you that it's performant and also that it's really fast, but here's some receipts. So the top set of graphs here is benchmarking on the SMAX suite in JAX-MARL. So this is the StarCraft multi-agent challenge, quite a famous benchmark in multi-agent RL. And as you can see, the straight lines in that graph are the benchmarks that are provided with their with the suite, with their paper. So it's the benchmarks that they obtained, and then the curves are what we obtain when running on the, with the same algorithm running on the same scenario. So in all cases, equal or better. And so you can trust that at least the algorithm should be working pretty well. And then the bottom graph is an interesting one. So we're less concerned with the performance here, but more with the speed. So this is the green and the orange line are MARL running on the JAX version of LBF, so level-based foraging, one of the ones I showed earlier. And then the blue line is a non-JAX-based framework running on the original non-JAX version of this environment. And as you can see, it's, MARL is basically a straight line here, just because it's a whole lot faster. So the x-axis is time in this case. Cool. Oh, I went too far. I'm back. There we go. Cool. So yeah, that's MARL, and where it fits in is it's kind of basically it's our starting point for research. So we use it. We take MARL, we fork it whenever we're embarking on a new multi-agent research project, and as a result of this, of course, we use it to create novel MARL algorithms, but also we continuously improve the framework. So we'll do kind of like a research sprint to, for whatever the project is. And then within that sprint, we might find, oh, we really didn't like this about MARL. And so we'll come back in and we'll change it to be specifically more researcher friendly. So that, next time we do a MARL project, there's a better starting point. Yeah, and that's kind of where MARL fits in. And I'll hand over to Callum to chat about flashbacks.
Thanks, Sasha. Hello, everyone. My name is Callum. I am a junior research engineer at InstaDeep. And yeah, I'm going to continue speaking about the ecosystem. Kind of we're at this place now where we have Jumanji, so we can JIT our environment and put that on the accelerator. We have Marvus, we have these wonderful on-policy algorithms, but there's still the question of, well, how do we do off-policy algorithms? If we trying to handle data, we want to have everything on the GPU, on the accelerator. What if we are, say, storing to a replay buffer? How do we integrate that into our ecosystem? And so there was this need for some sort of JAX native accelerator-oriented replay buffer library, and that is essentially what flashbacks is. And flashbacks is a set of tools and utilities for replay buffers at JAX. And along with that is a utility called Vault, and I'll just discuss them briefly now. And this is a really come out of the need in MARL for off-policy algorithms. So flashbacks is pip installable. It is this very lightweight library. It's meant to be short and to the point, exactly what you need. And yeah, very, very easy to use, where it's pip installable, you import it as normal. And the important thing is that it's purely functional. And now this might be a bit strange compared to a typical feeling around, say, a buffer, where there's this natural idea of an object, right? A buffer having some sort of state. And so in other replay buffer libraries, you might have buffer.add and you just kind of give it your new data. Whereas here, because we wanted to still fit into this functional JAX paradigm, we need to pass state around explicitly. And so when we create the buffer, all we're getting then is actually just the set of pure functions. And so we have a trajectory buffer, for example, which can store trajectories, time steps in a row. And so we create these pure functions. And then we need to get an initial state. So we initialize with an example time step, and now we have this state. And every time we do something with the buffer, we need to give in the state and then receive the new state. So this is this functional paradigm, which might take a little bit of time to get used to, but it actually has huge benefits. So say now we have the buffer add function. Because it's functional, we now can give it the state, we get the new state back. Now we can just in time compile this whole add function. And there's also efficient memory management. So we can say, to JAX, don't reallocate new memory for the state. The state is the same thing that we had before, but this makes it very, very fast. And so this is how we add data, and the sampling is also jittable and also very, very fast. And you'll see there's also random number RNG key there, which is, as Sasha mentioned earlier, it's these reproducible rollouts, so pseudo-random, but deterministic pseudo-randomness, which is beneficial for reproducibility in our research. And so this is the flashbacks library, and it allows us to essentially use replay buffers on the GPU, on the TPU, which makes it incredibly fast and makes our off-policy algorithms very efficient. Now, say you're using flashbacks and you have these buffers, sometimes we want to save that data. And that might be that we are checkpointing a large run that's lasting a long time. Or very naturally, we might want to save our experience data in our buffer, which we then use as static data in a later setting, which is offline reinforcement learning, right? And we'll chat more about that in a second. But to do that, we have this very, very lightweight utility called Vault, and this all exists in a single file. And it's meant to just attach onto flashbacks in a very simple way. So we import the Vault and we create it with some sort of experience structure. So we give it the flashbacks state, and periodically we write to the Vault. And the basic idea here is that we want to do the very efficient thing on the GPU for a certain number of time steps. So we train for, say, 1 million time steps, we populate the buffer, and that's all happening on the GPU. And every now and then we can exit that jittered context and write to disk. And writing to disk is the slow bit, right? And so every now and then we write to disk, and then we go back into the jittered context, we generate more data, we exit the context, write more to disk. And this is what the Vault utility does for you, but it does all that bookkeeping. So provided you write regularly enough, you just give it your flashbacks buffer state, and it'll just write anything that it hasn't seen before. And so we found this to be a very, very useful utility for creating data sets from our RL experiments, which we then use later. And what's nice is because it's so naturally coupled with flashbacks, using that data at a later stage is trivial. So we have a Vault now written, we read it in and we say, okay, we want the second half of this data. We read it in through the simple vault.read. And now we have a buffer state, which is exactly equivalent to a flashbacks buffer state, which we can use in the same context as before, where we sample from it or we add to it further, and so on. And so these two utilities allow us to essentially create replay buffers and data sets from our experiments. And this is kind of how it fits in then to the broader ecosystem. So we have Jumanji plugging into Marva on the accelerator. And now because of flashbacks, we can have off-policy algorithms. And then also we can have data recording, which then goes to disk. Now, naturally, the follow-up thing is we've got all this data. We can now use that for offline multi-agent reinforcement learning. And so whereas flashbacks and Vault are on that software tooling axis, we also want an easy starting point for offline MARL research. Now, offline MARL is a bit more of a nascent field, but some very, very exciting stuff happening, and our team has done some cool contributions. So OG MARL, off the grid MARL, is a suite of data sets and baselines in offline MARL. And this is offline MARL, just in case you weren't familiar. So that part on the left is when we're collecting the data. Say that's using Marva on a GPU. We're generating all that data, and we have then that data set. And then at some point, we actually unplug, and we no longer act in the simulator, or perhaps actually getting online demonstrations is too dangerous or too expensive. We just have a data set. And what we want to do is we say, we want to learn optimal control, sequential control policies from that data set alone. And that's the orange part where we're actually not able to generate new data or test out our policies in an online setting. And that's offline MARL. And what the team found when they were getting into this field maybe 2 or 3 years ago was that there were all these environments and all these things, but it hadn't really been standardized. And so we sat down, generated a standard set of data sets where we were clear about how we generated them, the environment configurations, and we did it across a range of scenarios. Everyone seemed to be focusing on SMAC, but it was very important that we learn a wide range of tasks and essentially challenges for our multi-agent problems. And so those were our data sets. And in addition to that, we also, not only do we offer the data sets, but we also allow you to then record your own data. So here we have an example where, say, we have a robot warehouse example from Jumanji, and suppose we now wanted to create a new data set. It's as simple as using the experience recorder wrapper. Now, what that might look like here is we have robot warehouse there in Jumanji, and we are essentially rolling out some sort of policy. We get observations, rewards, we take actions, and we step the environment. Now, that can happen very, very quickly. We write that to now a Vault through flashbacks, and now we have a data set, and that's very, very easy to use through the experience recorder. In addition, we have baselines, and these baselines are very easy to use. They're stable and tested, and that allows a really nice, solid starting point for offline MARL research. And this, as Sasha mentioned earlier with Marva, because it's in that middle pillar, what we want is for people to clone the repo and hack it, see what happens if we change various parts of the algorithm. We really want people to get in and use these algorithms, not abstract it away. It also follows the single file methodology. And what this baseline algorithm might look like is you load in a Vault, and that's all natively native with JAX. and these based on algorithm implementations, and then we evaluate online to see how our algorithms are doing. And as a fun little quick side note, that these algorithms are good, and we've recently done some work. We found that our baselines, even the simple baselines, can actually achieve state-of-the-art results on many, many scenarios. Just the baselines, not even, you know, some of these other advances that have been proposed. And so you can know that these baselines are good, they're robust, they're rigorous. And we really wanted to do good science around this, such that we can build strong foundations and do good research. And so that's OGMARL. And the way it fits into this broader ecosystem is that it's also sitting in this middle block, coupled with Marvin in that middle section, plugging into flashbacks and then plugging into this broader thing. And one of the artifacts now that we have on the right-hand side is these offline MARL datasets, which we share openly with the community. Now, out of both of these middle things, Marva and OGMARL, we have a lot of data. We have a lot of experiment data. And so Ruan's going to chat to you about our next tool, which is MARL Eval.
Thanks so much, Callum. Yeah, really, MARL Eval is this tool that we built to try, and it actually stemmed from a very similar thing that was found in the offline multi-agent RL case, but in the single agent RL case as well. We really have a desire to push for standardization in the field so that we can, as a community, drive the field forward. And sort of MARL Eval, this aggregation tool, was really built off of exactly this desire that we had and some work that went around this. So given all of this data, we want a nice way, in a statistically robust way, to aggregate everything. And actually, Agarwal et al., they released a paper at NeurIPS in 2021, and I actually believe he was the speaker here just last week. And so following on from the work that they've done, we built this abstraction on top of what they made, which, given your data in some standardized format, can produce these aggregated score plots and can produce sample efficiency curves for you. It can produce these performance profiles for you, and it can produce these probability of improvement scores where you can really see if one algorithm is improving over another. Of course, to be able to do this, or to be able to build this like abstraction tool to aggregate data for you, we called for a standardized way that this experiment data should be logged in this JSON format. But we know that this can be rather tedious. And so following on from work that was done by Benchmark, we wrote the JSON logger that can write all of your experiment data in the required format for you. So as an example here, we're using this JSON logger, we're plugging it into Marva, and it's producing exactly the format of data that we want, so that we can carry on and use these MARL Eval tools, which simply means you process your data with some functions and utilities that we offer. And once this data is processed, you can really easily produce these probability of improvement scores, or as an example here, also these aggregated score plots. And so this is where MARL Eval fits into this entire ecosystem, where it can use this experiment data that's generated by the algorithms in Marva and OGMARL, and it can produce these statistically robust benchmarks and baselines, which we can trust. And as a community, we can push the field forward together. And that really sort of brings us to the final pillar of the final aspect of the community artifacts pillar, which is impactful and reproducible research. So as a refresher on this entire ecosystem's pillars, the first pillar being stable and maintained software tools, which comprise of Jumanji, which are these RL environments, flashbacks and Vault, which are these jittable replay buffers and data storage tools, MARL Eval, which is this experiment data aggregation tool, these easy starting points for research in Marva and OGMARL, which really are there for the community, but also for ourselves to start and hack with and build research on, but that we know once we've done our research, the software can also scale to leverage massive compute and new accelerators. And then our final pillar, which is these community artifacts, which is research that we believe will be impactful and reproducible and beneficial to the community as a whole. So to summarize, here's our entire ecosystem, but we don't just want to leave you there. We really want to show just a simple example of what using this entire ecosystem together can do, and the avenues of research that this can open up. So for example, you could take an environment from Jumanji. In this case, we're using the robot warehouse environment. You could train an algorithm in Mava, and because it's in JAX, it'll be really, really nice and fast. So for example, here with this example, we trained it on a laptop GPU in a couple of minutes. And then you can store your data in these flashbacks vaults. And once you have them stored, you can load them into MARL, and you can train some offline algorithm. And you can do all of this in a statistically robust way, so that when you do research, you can make nice claims, and your research can be reproduced as well. Now really, this example, our desire with this example is really not to show that we can train small scale 4-agent environments really, really fast. Our desire with this example is really what it opens up. What could we do if we had, for example, hundreds of agents? Or what could we do if we had data sets that didn't only contain data from a single task or even from a single environment, but what if we had massive data sets? What are the sort of work that we can do? And so with that, this is the InstaDeep multi-agent RL ecosystem. We're really so thankful that you had us. And if you have any questions, we'd be more than happy to answer them.
Great, we have lots of time for questions. Anyone have a question can speak up or type in a chat. So what was difficult in building up this ecosystem? Which part, I don't know, took the most time, or what kind of difficulties did you guys encounter?
The first one that I can speak of is Mava. So to begin, I think Mava is actually in its third iteration right now. Building out frameworks is extremely challenging. And in fact, when Mava started, I think Mava started around 4 or 5 years ago. It was actually a framework built exclusively on TensorFlow, and used distributing techniques, but we found that like distributing these algorithms were really, really difficult, and we made made design choices that downstream was really, really proved to not be so useful. So then it was lesson number 1 is don't try and over optimize or over modularize your code for a hypothetical user that might want to do some esoteric multi-agent RL thing. So then we decided, okay, let's pivot from there. It's actually along the same vein of mistakes. We felt, let's pivot from there and make something that was even more general. So instead of just having a framework, we added in callbacks to the framework, and the idea in principle made a lot of sense. You could plug in any component that you really wanted to. But then as a company, we took a hard bet on pivoting to JAX. And for anyone who has experience developing in JAX, maybe you share my pain, but I can definitely share that trying to do callbacks while trying to do JAX is very, very difficult. It proved to be extremely challenging in the way that things were set up, which in principle would have enabled us to do research really, really easily, but it proved to be very hard to maintain and to engineer up. And so that's why we made this switch to what Mava is right now, where we adopt this philosophy that's very similar to what's been done with CleanRL. And then as a consequence to that, pure JAX-RL, where really the goal is to have all of these algorithms contained in a single file, which is really easy for someone to look at and to do research with. So the one I can say is the most tough, purely because it took the longest, was building Mava into what it is right now, where it's something that we're not only proud of and excited for other people to use, but something that we really use day to day for our own research, and it's taken away loads of friction. Yeah.
I just want to add to that, that we talk about this a little bit in the Mava technical report, that when you're designing research software, there's this challenge between making something that is fast enough to do meaningful research in a short time span, like a reasonable time span. You can have a completely transparent algorithm where every step is like super clear and it's super readable, but then it takes years and years to run any experiment. So you have that tension on the one side, and then on the other being you know, an algorithm that is ridiculously fast, but so opaque that if you want to change one thing, it's incredibly difficult. And so someone could hand you a PPO that, you know, runs 1 billion steps a second, but now suddenly you want to adapt anything and it's way too difficult. And I think that this is the ongoing tension that I think any research lab faces. But we've certainly wrestled with, and we eventually just you find a midpoint that suits you and that is good for your research. And I think that that's been an interesting challenge, finding code that is fast enough to do meaningful research in a reasonable time frame, but also easily understandable and not too opaque that you can actually meaningfully build on it and extend it. And that's what we hope Marva is, and all these tools are at this point, and that they find that balance. There's also a question in the chat, which I'll take a stab at, and if anyone else, Ruan or Sasha, if you want to add. But Jesse asks, are there any other libraries for RL using JAX on accelerators that you would recommend? I've wanted to use INF's like DeepMind Control Suite, though they say they have no plans to support the new MJX standard. So off the top of my head, I mean, I feel like I see a new thing on Twitter every day. But recently I've seen that CraftAx was recently accepted, I think at ICML or ICLR, and they look like they're doing some really cool things. And then, yeah, some of the other things mentioned in this talk. So I think that, you know, the Oxford group is doing some cool stuff with JAX MARL, and then there's also some other things linked on, I think, like the Jumanji repo, some of the other environment suites. I think there's one group that has done, rather than the kind of environments we're doing, they've done things like chess and shogi and Go and whatnot. And then I don't know if you want to add anything, Ruan or Sasha?
Yeah, for sure. Something else so we touched on a architecture for using JAX in reinforcement learning, which we refer to as the Anakin architecture. But in fact, there's a whole other architecture. So Anakin has the benefit that it's extremely fast because you have a JAX-based environment and a JAX-based algorithm, and everything is end-to-end jittable and really, really, really fast. But there's another architecture called Sabalba, with like the nice Star Wars references there. But essentially what Sabalba enables you to do is, if your environment's not written in JAX, you can in fact run your environment on CPU, and then you can run your learning on a TPU or a GPU or some accelerator like this, where you get sort of the best of both worlds, where you can run many, many environments in parallel, but still train extremely fast. For examples of the Sabalba implementation, if you go to InstaDeep's GitHub, we actually have an open source implementation of Sabalba, which trains really, really fast. There's a blog post that we did together with Google on scaling up training PCB circuit board routing environments really, really fast on TPUs. So there's an example of that. If you are very interested in following actively with what we're up to, we're actually in the process of implementing Sabalba in Marva. So if you want to do multi-agent RL research on environments that are not in JAX, soon you'll be able to do that with Marva as well. And then there's a really nice implementation by Costa that made CleanRL. He also has an implementation called CleanBA, which is essentially single file implementations of Sabalba, of this exact architecture as well, for reinforcement learning research.
And just to add to that as well, if you're looking to do single agent RL and not multi-agent RL, there's actually a fork of Marva called Stoix, S-T-O-A-X. So it's maintained by someone here at InstaDeep in his personal capacity. But yeah, it gives you pretty much all the benefits of Marva, but it's single agent RL if you're looking to do that.
Yeah, for sure. There's another question by Randy. What are additional challenges or considerations that doing multi-agent add to the framework development versus single agent? Great question. There are a few challenges actually. Well, so at the moment, we focus on cooperative multi-agent reinforcement learning, where some team is trying to work together to achieve some goal. And so Marva is really engineered with this at heart, because the problems that we care about are fundamentally cooperative to begin with. But a standard challenge that comes when you're trying to build a framework for multi-agent RL is, firstly, what multi-agent paradigm do you want to support? Do you want to support cooperative multi-agent RL? Do you want to support competitive multi-agent RL, or some mix between the two? And so we've decided to support cooperative multi-agent RL. Then there's a few extra questions that you maybe want to consider. Do you want to implement communication in your algorithms or not? We're hoping to. So that we're really trying to make as easy as possible by exposing all of our logic. Another challenge is how would you support environments where agents enter and leave an episode, for example? But these are some extra considerations that we handle as we need them. Right now, since we're focused on homogeneous, where all the agents are the same, and cooperative multi-agent RL, this is what Mava is geared towards right now. Next question that I'll read, and then maybe someone else can take it from there. But AZ says, great presentation and awesome work. 2 questions. Do you have any examples in these repos of evaluating offline RL policies on counterfactual data? For example, while learning a policy, also learn a world model / simulator that then uses the policy in the simulator to test new episodes. Callum can also expand on this a little bit, but no, we don't have any examples of this. But the way that we do evaluate algorithms right now in MARL is that we train them exclusively online. So the algorithm is just trained on the data, but then when the algorithm is evaluated, we evaluate it in the simulator, which is the closest to what you're describing. Hey? Train. Oh, my bad. I said train online apparently, but I mean train offline and then evaluate them in online environment. Do you think some of these repos could be used for offline RLHF work, i.e. DPS, not preference learning? I'm not very familiar with RLHF, like implementing RLHF to begin with. So perhaps my answer is slightly naive here, but what I do believe is if you can implement an environment style API, something that does like an action and a step and a reward and done signals, I think you could use it for sure. Should actually be quite nice, because maybe doing RLHF, like if you have access to nice accelerators, you could make that whole sort of environment loop jittable, because it's a supervised learning problem firstly. So it could be quite cool, but I don't know how easy or hard that will be.
Sorry, thanks, Carl. Just to jump in to that first question from AZ, just as a general thought, it's quite a involved process that you're describing here. And I think what's really nice about Mava and just the general kind of clean RL style of writing frameworks is that it really exposes all the logic to you. So while we don't learn a model, a world model, we do have the policy learning there. And so you could take that policy learning as a starting point and implement, learning a world model, with using, let's say, PPOs as a starting point where the PPO stuff works, and you implement the world model around that. So yeah, that's an option, and why we decided to go this route with this framework.
One other thing I wanted to add, and this I think applies to all the questions that you may ask or maybe just be thinking about. This last slide that we have is a link to all these repos, and we just want to really encourage people to engage here and go to the GitHub repos, give them a star, and then ask us questions, open up issues. If there's any questions about what we are implementing or plan to implement and whether we do, or if they're bugs, each of these projects has people working on them at InstaDeep, and we use them, as we said, every day. And so we really want the community to be involved in this. And this is why we are doing this presentation, really. We want people to engage and to contribute. And so, the questions from AZ, these are the things that you can ask on the repo, say on MARL, and we can, kind of give a bit more of a detailed answer. And then coupled with that, say, okay, well, what kind of things would be required for this to happen? And whether that's a fork of the repo or whether that's actually a core functionality, we're certainly open to all of this. And we really just want more research to come out of our tools and for people to build on these things. And so I really encourage and urge everyone to engage, and please, you know, ask us questions and pester us with bugs and all that kind of stuff. I see that there's another question from David Murphy. Any thoughts on translating existing offline RL datasets into your Vault format so one can may carry on in your framework? So that's actually a fantastic question, and I'm smiling because it's recently we've actually done some of that work, and it's under review. No guesses of where it's under review, but it's been quite recent, and we've actually been undertaking this effort. And so we do feel like what offline MARL needs, offline RL in general needs, is standardized data sets and baselines. But of course, there's this reality of existing data sets that we want to be able to use. And so we've now started using the Vault framework to convert these things, and they will be public. And we'll also be sharing our results in them. But what's really nice, and I truly do believe this, that Vault is such a nice format where if you look at a lot of the other offline MARL data sets, I can't speak for all offline RL, but offline MARL data sets, researchers will often just dump a huge folder of NumPy data sets, NPY files, and just hope that you know how to unpack them all and make sure that you have everything and sort it all out. Whereas, as I showed earlier, Vault is as simple as saying, Vault, you point to the Vault where it is on your disk, and you say, Vault.read, and it reads it into a native flashbacks buffer with the experience structure there. You can use it straight away to sample or anything like that. So you don't need to assemble the data sets at all. And so we've done some offline MARL data sets now, but I see your question actually says offline RL. And so that's certainly something we could look at doing in the future as well. We feel like just the API works very, very well with our systems. And yeah, but exciting, and very happy to share that work in time. Thanks for the question. This is the part of the talk when I feel like I must say like and subscribe, but instead of like and subscribe, it's, you know, scan and star.
And use them. Maybe a bit of a forward-looking question. So now we have this whole ecosystem set up. What's the next thing that you think people, when they check it out, what's the one small research idea people can start playing with, or start contributing to this, to the library?
Yeah, so the one thing that I think it's been on our mind, and I'm quite excited about going forward, is that middle column of Marva, OG-MARL. We presented them as separate, but really the integration of the two. So offline to online, online to offline, and you could imagine, you know, kind of actually loops of this where you have a very, you know, the more expensive simulator, and say you train that with a Sebulba thing. So it's a non-JAX simulator, and you do some offline, online training within that simulator in the Sebulba architecture. So it's still fast, but it's not as fast as you would like it to be. But then in that process, you write some data to disk through Vault, and then you have an offline training procedure where you can learn some better policies. And then maybe you could deploy those policies. And so you essentially are online, but you're just delaying that online step a little bit more, and you're making it a little bit more off policy. And so I think that there's some cool stuff there. There was a workshop at ICLR last year called Reincarnating RL. And there was this whole flavor of how can we reuse prior computation. And I think one of the exciting things was indeed not just the one direction, not just saying, can we learn, you know, offline from a previously trained online policy, but can we, you know, reincarnate a policy that we've learned a little bit offline, we put it online. And really, you can imagine all sorts of permutations. And so that's, I think, something that I personally feel quite excited about, and I think the team is excited about. And what's so nice is that with this framework, with these sets of tools, you know, we are presenting them as 5 separate repos here. And if you are only wanting to use Jumanji, that's fine. It's, you know, we're not going to criticize you for that. That's fine. If Jumanji suits your research needs, then that's completely cool. But what we really say is an attractive feature of the whole ecosystem is that everything plugs in nicely together. And so, you know, flashbacks and Vault plug very nicely into OG MARL, which plugs very nicely into Marva, which plugs very nicely into Jumanji, and all of that goes into MARL eval very nicely. And so the hope is that these kinds of paradigms, this offline to online, previously may have been a bit janky because you're using in one system and now you have to go to another system. The hope is that these things are really a lot more frictionless going forward. I don't know if you guys want to add anything.
Is it ongoing work or is it already done? Because I didn't check the links thoroughly, of benchmarking existing algorithms and see how they work, maybe having
So in the offline
of some kind of leaderboard.
Yeah, so we don't have a leaderboard per se. In the offline case, there's been some extensive benchmarking, just because I think more so because there was a need for that. And that's work that if you go to the OG MARL repo, there's a paper that was, I think, an extended abstracted ARMAS where there was some benchmarking that was done. And then Ruan can speak to the online case.
I think that would be amazing. If someone wants to contribute to that, it would be phenomenal. We are, of course, when we're working on research, we're working on some research right now, which of course requires us to run baseline experiments. And so we did run a lot of baselines over the last couple of months. And the hope is really that as we start publishing these papers and things start to slow down a little bit, our hope is really to actually make these benchmarking results publicly available. So things like hyperparameters and the tuning process that we followed and some of these plots and things. But I think that would be immensely valuable from the community. And then something else that I just personally find this very interesting is there's been really interesting work done in multi-agent reinforcement learning recently on heterogeneous agent reinforcement learning or heterogeneous agent learning. And there are these extensions to multi-agent PPO, which is called heterogeneous agent PPO. And I think that it's less a research thing that someone could do, but I more feel like it's a fun thing that someone could do. Like if you change PPO to be heterogeneous agent PPO, I think that could be quite a fun thing and something that shouldn't be too tough to implement as things stand at the moment.
So if someone did produce some benchmark, what's the best way to interact with you guys? So pull requests or write a paper? What do you think?
I think the way that we'll probably respond fastest is issues on the repo and pull requests.
Okay.
We really welcome that.
It's really satisfying seeing a tool being well made, so that now it's empowering researchers to do more things. In my own research, I'm always constantly frustrated by what tools are available for some small thing I want to do, but just I have to jump through so many hoops to just do that one thing.
It's very encouraging, and it makes me very happy to hear that. Yeah, it makes us really glad. It's something that's really our desire here, is to build tools that we really like, but that will really benefit the community as well.
Yeah, and it's good to hear that you are using it actively, because I've seen many tools being made and just like dumped on GitHub, and they don't really use it, so they don't really maintain it. I mean, it's better than nothing, but those still, it's a bit disappointing. So good to hear that
we're using it. Sorry, we're using it as we speak. I'm busy running experiments with like research that are forked off of Marva right now as we speak.
Cool. Great. Look forward to see what comes out of it from the community using this tool, and what further features and stuff you added to the tool. You're always welcome to come back and give an additional feature talk. Right. Thank you, Ruan, Sasha, and Callum for giving the great talk, and David for staying here this whole time. Great. Thanks, everyone.
Thank you so much, and thanks so much.
Thanks so much.
Bye.
Bye-bye.